All right, number 7 is a doozy. We need to, in order to combine these two fractions together, we need to make sure, through subtraction, we need to make sure that we have the same denominator for both of these guys. And the way that we determine that we have the same denominator is we have to multiply by the other fraction's denominator. So we have a common denominator between the two of them. So I'm going to multiply this whole fraction by 2 plus the square root of 5 and 2 plus the square root of 5, top and bottom. And then I'm going to multiply this fraction by 2 minus the square root of 5 on top and bottom. So foiling out the numerators here, let me write it out so it looks nicely. So I need to FOIL out the numerator here. So I get 4 plus 2 square root of 5 plus 2 square root of 5 plus 5 all over. And I remember that this is going to be 4 minus 5, right? The square of the first term minus the square of the second term. Minus, I'm going to distribute that square root of 5, so that becomes 2 square root of 5. Realize that this minus is being applied to both pieces. So it's negative square root of 5 being multiplied to this guy. So it's going to be minus, keep that in mind, and then we'll figure that out later as well. I changed my mind. So we're just going to distribute square root of 5. So that's just 2 square root of 5 and then minus 5. And then we'll just remember that there's a subtraction still here, which needs to be distributed to both of the terms in the numerator. And then it's going to be 4 minus 5. So I'm going to put parentheses in my numerator. I've got 4 plus, this is going to be 4 square root of 5. Because we've got 2 of the square root of 5s and then another 2 of the square root of 5s. So they combine together to be 4 of those. We can think of it as a variable. That if we have 2x here and 2x here, they would combine to be 4x. Oh, and this 4 and the 5 combine to be 9. So I'm going to do 9 plus 4 square root of 5. I'm going to do minus 2 square root of 5. And then a subtraction of a negative is going to turn into a plus here. And then my denominator, my common denominator, actually ends up just being negative 1. All right, now I just need to combine my numerators together, my numerator pieces together. I've got 9 plus 5, which is 14. And I've got 4 square root of 5 minus 2 square root of 5, and that's going to be a positive 2 square root of 5. And it's still divided by negative 1. When we are dividing out with this one number here in the denominator, just like when we are combining fractions together, where this had the same denominator, and then when they combined together in the same denominator, we really just took the two numerators and pieced them together under the same one. And so going backwards, right, we would have had to split each of these guys up and then take this denominator and put them under both of them, right? If this was negative 1 and this was negative 1, they combine together in the numerator like this. So moving backwards, we would take each of those pieces and separate them out, with the numerator being split and being put underneath each of them. So moving backwards from here, I have two terms. If I wanted to split them up into two separate fractions, I would need to make sure that they each have the same denominator. So that denominator needs to be applied to both of them, because when you're adding or subtracting fractions, they need to have the same denominator in order to combine underneath. All right, so we keep that in mind to remember that then this is going to be negative 14 and then minus 2 square root of 5. That one is a doozy. This is kind of where we're going with all of that we've been learning so far about radicals. This type of problem is where we're going to. This is also something that will continue to pop up in 10th grade, 11th and 12th grade, okay? So this is something that's going to be used a lot. The main idea is that we needed to have the same denominator. It just so happened, and they tend to happen like this a lot, that the opposite denominator was the conjugate. And so since the conjugate then made it really nice for it to all come out and there was no radical in the denominator, we could combine them all together and make it work. All right. Problem number 8 is a problem that is a little bit tricky, and I just want you to realize that you can totally figure it out, and we're going to try and figure it out together and puzzle it out. So this is definitely a challenge problem. So it says that we have this radical, or we also call them a surd, S-U-R-D, that is radicals within radicals, and it wants us to write it in this form, a plus b times the square root of 3, where a and b are integers, meaning that they're these whole numbers that we can that we use, as you can see, in front of all these radicals. So the main idea here is that if we've got a whole square root over this, this expression, and then it can be written in this way with no square root over the top, and a and b are integers, that means that whatever is happening inside of this square root is a perfect square in some way. It means that we had something, a plus b times the square root of 3, squared such that it came out to be a plus b times the square root of 3. Does that make sense? That as long as we have this whole thing in here squared, and then we take the square root of it, that is the only way that then it could come out to be a plus b times the square root of 3. So in the context of this problem saying, hey, here's this thing, and write it in this form, it's telling you this is a situation such that if we take the square root of it, it comes out to an integer, meaning that this must be some sort of situation like this. So keeping that in mind, that means that a plus b times the square root of 3 squared must be equal to 28 plus 16 times the square root of 3. So keeping that in mind, we are going to figure out what is a plus b times the square root of 3 squared. We are going to FOIL it out. A plus b times the square root of 3 times a plus b times the square root of 3. First times first, outside times outside, inside times inside, and then last times last. Combining like terms, a squared plus, these guys can combine together to be 2ab square root of 3. We've got one of them here and one of them here. Adding it together, we now have 2. And then I'm going to make this 3b squared. Now I want this term right here to look like this term, or sorry, look like this term right here, which means that I want my square root of 3 term to be at the end and by itself, and that's this term. Okay, so this guy kind of matches up in the foundation of this expression, where it's this number being multiplied to square root of 3. It needs to be equal to this number multiplied by the square root of 3. Now we've got a squared and 3b squared that add together that don't have a square root of 3 on it, which means that it needs to match up with 28. So rewriting it, I'm going to do a squared plus 3b squared plus 2ab square root of 3. And that must be equal to, not 18, but 28 plus 16 times the square root of 3. So a squared plus 3b squared must be equal to 28. 2ab square root of 3 must be equal to 16 square root of 3. So from this, we can find out what the relationship is here. I know that a squared plus 3b squared must be equal to 28. And I know that 2ab must be equal to 16, okay? I'm going to leave out the square root of 3 because I know that that has to stay there. So I know that this coefficient right here, 16, must be gotten by multiplying this idea of a and b and multiplying it by 2. So I have ab, I divide both sides by 2, must be equal to 8. And since a and b are integers, we actually only have a couple options for two numbers that multiply to 8. A could be 1 and b could be 8, or a could be 8 and b could be 1. We could also have a be 2 and b be 4, or A be 4 and A, oh my gosh, so sorry. Okay, or A equals 4 or B equals 2. So those are our options for pairing these guys up. Okay, so what we've done so far is we've noticed that these guys, if it comes out to be this, that means that what's in here must be that guy squared in order for that radical to just go away. So we said, okay, well, that guy squared must be equal to the radicand that's in there right now, that piece that's under the radical right now. So then I FOILed it out to try and get it to look like what is inside, to be able to match up pieces and create an equality between these two radicals. Then I broke it down into pieces again. I said, well, hey, this expression right here must be equal to this expression right here, and this expression right here must be equal to this expression right here if it were to be rewritten in this form. So then, using this, I said, hey, a times b equals 8. There's only so many options, whereas like a squared plus 3b squared equals 28. That could be a lot of options. So I'd rather start with this and try and piece it together. What of these pairs will give us this as well, will agree with this? If I plug in 1 for a, that'll be 1 plus b squared is 64. Multiply it by 3 and then add 1. That's automatically, we know, going to be over 28. Also thinking about it, if a was 8, that would be 64, automatically too big to fit into this equation. So that one doesn't work either. 2 squared would be 4 plus 3. B squared is 16, so times 3 is 30, 42. Yeah. No. Bigger than 28. 16 plus, and then 4 times 3 is 12, so 12 plus 16 is 28, and we have a winner. A must be 4 and B must be 2 in order for it to fit both this equation and this equation to be able to match up accordingly. So that means that the square root of 28 plus 16 square root of 3 can be rewritten in the form where A is 4 plus 2 for B and then square root of 3. You could always double check it by squaring that guy and hoping that it gives you 28 plus 16 square root of 3. This is kind of a hint and an insight to some of the lessons that are coming up where we talk about something called equality of surds. And this is the idea of how to do it. All right, guys, good job today.